Good evening. Welcome back to AP Stats Notes Online. Going to get into section 8.3 tonight. And 8.3 is all about trying to estimate a population mean. So we're going to move away from proportions for a little bit and get into our sample means to help us estimate the population mean, or a population mean, whatever mean it is that we want to try to get. Before we get there, I want to quickly sort of review, not review, but talk about how to choose an appropriate sample size when we plan to calculate a confidence interval for a mean, right? This was the tail end of what we did for proportions, but since we just talked about it, I want to go ahead and cover that first now. And so, how are we going to go about doing that? And we're going to skip the first question in your notes and get to the second question here and talk about that. Okay, and so choosing a particular sample size is going to depend on what kind of margin of error you want to have in your study, right? That's what we did for proportions. We'll do the same thing now, right? So how much margin of error are you willing to accept? Right? This is not very good English there, but anyway. Well, how do you go about calculating margin of error? Remember, from confidence intervals, it's statistic plus or minus critical value times standard deviation of the statistic, or standard deviation of the statistic. This part is your margin of error. Okay? For means, for sample means, trying to estimate a population mean, what do these look like? Well, critical value that we talked about before was your Z star, okay? And then the standard deviation of your statistic looks a little bit different when you're working with means, right? That is the standard deviation of the population divided by the square root of your sample size, okay? So this is what we're going to work with your margin of error. So that being said, I'll get rid of this and show you how we're going to answer the question there. How do we choose an appropriate sample size? It's a lot like what we did for proportions, only we're going to change that one calculation, right? So we're going to set a margin of error and make sure that our calculation for margin of error in our interval does not exceed it. So whatever it is, if I want a margin of error of 2.5 or 3.7, because maybe we're talking about means, right? So I'm going to take that margin of error, say I want it to be 2.5. I'm just making that up. That doesn't come from anywhere. I don't want this calculation to be any bigger than 2.5. That's the biggest margin of error I want to have. I'll take a smaller margin of error if I can get it, but that's as big as I want it. Now, if it's, say, for a 95% confidence level, then we already know what Z star is. It's 1.96. We would have to know the population standard deviation, and that can be whatever, right? 0.2. I don't know. I'm just making that up. And then we have to go through and solve for n. Okay? A lot like what we did, again, for our proportions. Just want to make sure that I emphasize enough that your standard deviation calculation is going to change a little bit. Okay? So let's take a look at a particular example on how we're going to go about doing this. Okay? All right. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu, remember that's your population mean, at the 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated that standard deviation of time spent on homework per week is about 154 minutes. Pilot study, that's important, and we're going to talk about this in just a second because we're talking about a margin of error in context of a confidence interval and trying to estimate a population mean, which means that we don't know the population mean. Okay? Well, we'll get to that in just a second. So a pilot study indicated the standard deviation of time spent on homework per week is about 154 minutes. And so we're going to piggyback off of that pilot study and try to figure out what sample size we need to estimate the actual population mean study time. So how many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence in a margin of error of at most 30 minutes. We're going to take our formula here, our little formula here, and plug in our numbers, right? So we don't want any more than 30 minutes of margin of error. Our critical value for a 90% confidence level is 1.645. You can go verify that, and you really should. I don't want to show that here. We've talked about that more than a couple of times. Our standard deviation of our population was found to be 154 minutes from a previous study, and then we have to go look for N, right? So how would you do this? This doesn't go into a lot of detail. What I would do is I would divide both sides by 1.645, get some number here. Then I would multiply both sides by the square root of N to move square root of N over here. Then I would take this number and divide it into 154, and then I would square both sides, right? That's kind of what they've done here. They've wrapped up everything into one big calculation, okay? But you have to have some algebra skills to solve for N here. But when you do, N is going to be greater than or equal to 71.3. That means that the administrators need to survey at least 72 students. Remember, we're always going to round up because we want to be conservative in our approach for our sample size, okay? So there is one issue with what we've just done, and that is the fact that in order to come up with a sample size, we have to know the population standard deviation, right? Our standard deviation of our statistic comes from sigma, which is our population standard deviation. Well, think about that. We're getting ready to talk about estimating the population mean, which means that we don't know the population mean. Well, if you don't have a mean, then you can't get a standard deviation. Remember, standard deviation is, on average, how far each observation is from the mean. If you don't have a mean, you don't know how far, on average, an observation is going to be away from the mean. So having sigma is not going to happen. We're probably not going to know what that is, okay? So we have a couple of options here as far as that goes. Will we ever calculate a confidence interval for a mean when the population standard deviation is known? And the answer to that question is no. No, probably not. Again, for the reason I just stated. If we don't know the population mean, then, if we don't know the population mean, then we're not going to know the standard deviation. So we have to use an estimate for the population standard deviation. And we can do that either from a similar study or a pilot study, and that's why I underlined pilot study there. Okay? But obviously that's not the same as knowing the population standard deviation. So again, this margin, this estimating sample size calculation is a little bit off, right? We're not going to have sigma, so we're going to have to use what we got. Okay? But it's this is a good time to talk about how to figure out what sample size you need to take. And like I said, we can use the standard deviation that was found from a similar study or from a pilot study, and that will help us. Okay? All right. When do we use the t-distribution? And before we get into that, I want to make sure that we make a connection here with our z statistic that I think we glossed over. And it's important to do that because it'll help us understand why we're talking about something called a t-distribution. Where did our z star come from? Remember, we talked about, that's rough. We talked about the fact that we're working in a sampling distribution. This is with our proportions, right? We're working with a sampling distribution where this is some p hat. Remember that actually a sampling distribution is just a collection of p hats, right? All of these underneath the curve are a bunch of p hats that are obtained from a bunch of samples of the same size from the same population, right? So when we talked about finding the z-score that corresponded to 95% of those p hats being in here, which was 1.96, we sort of glossed over the fact that this 1.96 is a z-score that corresponds to an actual p hat. This is an actual p hat value, right? So if you remember, we take an actual value and convert it down to a z-score as a way to standardize things, right? And to get the z-score, we had to take the actual p hat minus the mean of the sampling distribution and divide that by the standard deviation, right? Which is going to be your, well, it would have been p, just bear with me, right? It would be 1 minus p all over n, okay? No problem. And there's not a whole lot of problem going from the actual p population proportion, which we're not going to know, to using the mean or the center of your sampling distribution. And there wasn't a whole lot of issues with knowing that we don't have the population parameter, so these p's are going to be replaced with p hats. Our sampling distribution doesn't really change shape in that instance. So we still use this approximately normal curve. We get into our standardized score, and we can use table A or inverse norm to get to our z star, okay? Consider that versus if we're going to do the same method when we're estimating a population mean. We still are going to talk about our sampling distribution. So this is for proportions. And this would be for means, right? So then our center here would be at something, some x bar, right? And we still want to find a standardized value that corresponds to 95% in here. Now theoretically that would still be 1.96, okay? But again, this is a standardized value that does correspond to some actual value of x bar. Remember that in repeated samples, x bar could be any value, right? How would we standardize this again? I mean, this is a z-score. How would we get this calculation? Well, we would take the x bar minus the population mean, right? And divide it by the standard deviation of the sampling distribution, which should be this. Okay, again, we're not going to know the population mean, so I would replace this with mu sub x bar, and I would have to replace, since I don't know the population mean, I don't know the population standard deviation, so I would have to use, instead of sigma, I would have to use the standard deviation of the sample that we get, S sub x. Okay? Now, if you don't quite get all of that, that's okay. Hopefully you were able to follow this for the most part, right? But the bottom line is this. There's an issue when we standardized our sampling distribution down to the standard normal curve. There's an issue with having to use the sampling standard deviation. The sample standard deviation. There's an issue. When we divide using by some number using the sample standard deviation, something interesting happens to our curve. Okay, the values, the way they shake out, the way they shape up, it's no longer anything that we can consider a normal curve. Okay, and if we need more explanation on that, we can go through that in more detail in class. Okay, but that's sort of a quick explanation, and the book will go through it with you as well. As you're reading the book, there'll be an explanation as to why a little bit more in your book. So when do we use what's called the t-distribution? Well, as I said, that sampling distribution, when you standardize it down, when you're talking about means, it's no longer a normal distribution, it's called a t-distribution. And so we use the t-distribution when we are using x bar and we don't know sigma, okay? Again, we have to use a sample standard deviation to standardize everything down, and the shape of our curve changes, okay? It changes into this thing called a t-distribution. So describe the shape, center, and spread of the t-distribution. Well, the shape is still going to be unimodal and symmetric. It'll look normal, but it won't quite be normal. The difference is there'll be heavier tails. And what we mean by heavier tails, the tails out here in the normal curve, right? What we mean by heavier is that there'll be more area in the tails. More area in the tails means more observations in the tails, which means, as the last sort of interpretation of this, means more probability in the tails, okay? So here, there's going to be more area in here than there is in a normal curve, okay? Therefore, it's going to have to be a little bit flatter, right? A little bit flatter, and the spread's going to be a little bit wider, okay? So the center is still going to be at 0. Okay, again, it's a standardized. This is what happens when we standardize all of those sample means. Okay, the center is still at 0. That's where the center is for any standardized curve, whether it's the z-scores or what we're going to call t-scores now. Right, t is a standardized score. The spread is going to be bigger than z. Like I said, since there's more area out here in these tails, it's still a density curve. We're still representing it with a density curve, and we know that the complete area under this curve has to be 100% or 1. So if there's more area in the tails, that means there's less area in the middle. And so the t curve won't come up quite as high as the normal curve will. It'll have to spread out some. So the spread is greater than z, right? But what is also interesting is that the t curve gets closer and closer to the z curve, right? The spread of our t distribution gets closer and closer to the normal distribution as the degrees of freedom increase, okay? Now, what do we mean by degrees of freedom? And for right now, I'll leave it off as the degrees of freedom is related to the sample size. Okay? Okay, degrees of freedom is related to the sample size. As a matter of fact, I'll go ahead and just let you in on where the degrees of freedom comes from, right? The degrees of freedom is always 1 less the sample size, okay? Whatever the sample size is, we subtract 1, and that becomes our degrees of freedom. So what that basically means is, as our sample size increases, our t-curve becomes more and more like a normal curve, okay? So let's talk a little bit about where this t-value is going to come from. And we'll explore the t-curve a little bit more in class with a small, quick activity, okay? But let's go talk about exactly how we want to go about finding this t-value in this t-distribution, okay? Suppose you wanted to construct a 90% confidence interval for the mean mu of a normal population based on an SRS of size 10. What critical value t star would you use, okay? So we're still going to use the idea of our confidence interval, which is statistic plus or minus. Now we have to have a critical value, okay, times the standard deviation of our sampling distribution, okay? Now again, our statistic is going to come from our sample mean, And this calculation now we know is going to have to come from the standard deviation of our sample divided by the square root of our sample size. Question is, where is this new critical value coming from? And it's not going to come from a normal curve. It comes from this t curve, so we call it t star. Okay? Now, how do we go find that t star? Okay? Well, we have a t-table that you have in the back of your book. It's also in your blue formula packet. Okay? So if you have that with you and you want to pull that out, you can stop the video real quick and get it. But I'm going to keep going here. So if you look, here's our table A, right? Area to the left. Looks familiar. After your table A, the two sides of your table A, we get into this next page, which is your t distribution critical values. Okay, now this works a little bit different than table A does. Remember, table A takes the z-scores, takes the critical values or the standard scores along the outside and corresponds that to a probability or a proportion under the curve. This is not quite that, okay? What this does is it cross-references your degrees of freedom, which is one less your sample size, with just the tail probability. How much area is going to be in the tail, okay? And this works a little bit like a normal curve, okay? And I'll show you what I'm talking about in just a second. So what we're going to do then is, and I'm going to bring this in a little bit, and so this, in the picture up here always tells you the upper tail probability. That's what we want to go find, okay? Well, if we draw this out, this is what we're talking about, okay? We're talking about some curve that looks pretty much like a normal curve, okay? Where I still am looking for some t-value, right? And we have it at 90%, right? Some t-value that corresponds to 90% being right here in the middle. Well, this is still a symmetric curve. So if 90% is in the middle, that means that you've got 10% in the outside in both tails, so the upper tail area is going to be 5%, or 0.05. Now our sample size was 10, so when we cross-reference our degrees of freedom with our upper tail probability, we go to 9, and we move over and find 0.05 in our table, which is right here. Okay? And so our degrees, our t star is going to be 1.833. So for a 90% confidence interval, at a degrees of freedom of 9, it's going to be 1.833. Now, for the same level of confidence, as our sample size increases, okay, then our critical value will decrease. Okay, and we get this from this trade-off we get in our margin of error calculation, and we can look at more detail later. Okay, but that's interesting to understand. All right, now next question is, what if you want to construct a 99% confidence interval from you using a sample of size 75? Okay? All right, well, we're going to do the same thing, right? We go back to our table here. Instead of 90% in here, we want 99% in here. Oops, let me move that up. Which means that we want 1% out in our tails, which means here we've got 0.5%, which means we're looking for 0.005. And this is at a degrees of freedom of theoretically 75 minus 1, which is 74. Okay? All right. Well, let's go take a look at our table. Look for degrees of freedom of 74. with an upper tail probability of 0.005. It's going to be this column right here. Okay? Well, I've got to scoot this up because we don't have our degrees of freedom captured in there. And look, your degrees of freedom start jumping. At 29, then 30, and then 40, 50, 60, 80, 100, and then 1,000. Okay? Well, you don't see 74. And that's a bit of a problem for us. Okay? So what do? Well, conventional wisdom says go conservative. If we have to make a decision, then we're going to choose for our margin of error to be larger than smaller. That way we can make sure that we capture that population mean. Okay? So we're going to be smack dab in between 60 and 80. Well, if you go over to your 0.005 and cross-reference down to your 60 to 80, you've got two values to choose from. Well, I want my margin of error to be a little bit bigger if I have to choose. That way, my interval's a little bit bigger, and I'm a little bit more likely to capture that population mean. So I'm going to round up through the table, round down in my degrees of freedom. So my degrees of freedom is technically 74. I'm going to use 60 and get a t-star value of 2.660. Okay? So using table B, you must go down to the closest degrees of freedom. Okay? All right. I'm going to keep moving here and get through the next couple of questions in your notes. Okay, so we talked about t-distribution, how to find our critical value there. So the rest of this becomes just a matter of putting together our confidence interval. Okay, so what's the formula for the standard error of the sample mean? Well, it's the same thing as proportions, right? We call this the standard error instead of the standard deviation. This comes from what we used as our standard deviation in our sampling distributions. It's just supposed to be sigma over the square root of n, but we've already discussed we're not going to know the population standard deviation. So we will, just like we wouldn't know p, and we had to use p hat in our standard error for the sample proportions, we're going to have to convert over and use the sample standard deviation in our standard deviation calculation for our sampling distribution. And so we're going to call that a standard error. Anytime our standard deviation comes from our sample data, we'll call it the standard error. Okay? So, again, it's the same as what we discussed with our confidence intervals for our proportions. Okay? So, that leads us to a one sample t interval, a one sample t confidence interval for a population mean, if we're going to estimate a population mean. And that formula looks like this, right? It's going to be x bar plus or minus t star times s sub x over the square root of n, okay? And again, this does tie into our general form of a confidence interval statistic plus or minus critical value times standard deviation of the statistic. Okay, so the connection here is this. Your statistic, if you're going to talk about means, is going to be x bar, your sample mean. Your critical value comes from this new t distribution, and this guy is our standard deviation of our statistic, now called standard error, right? All right, well, just like before, there are some conditions that we have to have met in order to construct a confidence interval for a population mean, right? And these are going to sound really, really familiar. Our data has to come from a random sample or randomized experiment, right? Same thing, we're going to look for SRSs, or randomly assigning our subjects to treatments, okay? Our sampling distribution needs to be normal. Now, how does that happen? Well, with means, it was different than with proportions. With proportions, we did n times p, or, a number of successes, number of failures bigger than 10. N times p bigger than 10, n times 1 minus p bigger than 10, where we had to use p hat if we didn't have p. For our means, if you think back to Chapter 7, sampling distributions, our sampling distribution for sample means was normal if our population was. It just kind of took on the same shape as our population. So it'll be approximately normal if our population is a normal distribution. If it's not normal, if our population is non-normal, then as long as our sample size is bigger than 30, central limit theorem kicks in and says that our sampling distribution will be approximately normal. Okay? And then of course, and again, these are, we can make the same tie to the 3 different areas of our confidence interval. Random makes X bar an unbiased estimator. Our sampling distribution being, normal gets us into a normal type curve. Again, that turns into a T-curve because we have to use S sub X in our standard deviation calculation, so that ties into our critical value. And then, of course, in order to use this standard deviation calculation, we have to make sure that our observations are independent. In other words, not sampling more than 10% of the population. All the same type of stuff. It just looks a little bit different as far as the normal condition is concerned. Okay? And that gets us into an example in creating a confidence interval. Okay, so let's go through that real quick, and we'll be in pretty good shape. Okay? All right, I'll cover this up so you're not writing too much as we go through this. Okay? All right, so principal at a large high school claims a student spent at least 10 hours per week doing homework on average. To investigate this claim, an AP Stats class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. The sample mean was 10.2 hours and the sample standard deviation was 4.2 hours. Construct and interpret a 95% confidence interval for the mean time that students at this school spent doing homework in the last week. And then we have a part B here. Based on your interval, what can you conclude about the principal's claim? Okay, because his claim is that our students spend at least 10 hours per week doing homework. We've got to keep that in mind. All right? So, 4-step process. State. Right? What do we want to estimate? Well, we want to estimate mu, and we got to define mu. It's the mean time spent doing homework in the last week for students at this school. We want to make sure that we include a confidence level, 95% confidence. Okay? Plan. Okay? State what you're going to do. Since we're working with means, we're going to do a 1 sample T interval, and now let's go check our conditions. Right? This is from an SRS, so the students were randomly selected. Okay? Random sample of 250. Our sample size is 250, so central limit theorem kicks in and says that our sampling distribution is of a shape where we can use our T procedures. Okay? And then independent, it's 250 students out of a large high school. We're a large high school, and we have more than 2,500 students with which we could choose from. So it's reasonable to believe that there are more than that many students in this school. Okay? So that's what our independent condition is going to look like. Right? Good. We're ready to go ahead and actually do our confidence interval. Okay? So, because there are 250 in our sample size, that means there's going to be 249 degrees of freedom. And we want 95% confidence. So if you go into table T, you're not going to find 249 in your table. So we're going to have to round down to 100 to get a critical value of T star of 1.984. You need to go verify that. Make sure you can go find that T star of 1.984. Okay? Now, that being said, we've got our X bar. We've got our T star now, and we've got our all the information we need to go do our interval. So from our sample of 250, the mean number of homework hours spent was 10.2. Our T star is 1.984. The standard deviation was given to us as 4.2 hours, and again, the sample size was 250, and now it just becomes arithmetic. And you do all the work out here, go ahead and add and subtract the margin of error to 10.2, and you get this interval here. And now we need a nice conclusion. So we are 95% confident that the interval of 9.67 to 10.73 hours captures the true mean number of hours that students at this school spent doing homework in the last week. Okay? Now, go back up to the Part B question. Based on your interval in Part A, what can you conclude about the principal's claim? And so you have to remember that the principal's claim was that students spend at least 10 hours doing homework, which means 10 hours or more, right? Well, since the interval of plausible values does include 10, it includes values bigger than 10, but it also includes values less than 10. So it's plausible to think that students spend less than 10 hours per week doing homework, but it's also plausible to suggest that students spend more than 10 hours doing homework per week. So based on this interval, it doesn't provide convincing evidence to support the principal's claim. Of course, we're not going to be able to refute it either, all right? And so that's how you want to use the interval to talk about the principal's claim. All right, we'll stop there, pick up more notes the next night, and wrap up 8.3 and really be ready to start wrapping up Chapter 8. Okay, take care, and we'll see you guys in class.